me, it's really an incredible thing that has happened in my lifetime.
There's some big unanswered questions about the universe out there, which we feel we will not be able to answer with the LHC. So the first phase of the FCC is build a tunnel and then put in an electron-positron machine. So this is enabling us to kind of do dedicated large-scale Higgs production, and as the physicists put it, study the hell out of the Higgs and really kind of look for any deviations from the standard model.
This will be one of 8 sites,
Exactly.
and this, most of them will be in France, I understand.
Yes, there are 8 surface sites in total. 1 will be in Switzerland, in the canton of Geneva. 7 will be in France, out of which 5 will be in Haute-Savoie, and 2 will be in Ain. And here, what you can see here is actually one of the potential surface sites for the future FCC.
How big will it be?
It will be typically 4 to 5 hectares per surface site.
This whole field?
This whole field here will be taken, not up to the forest, but up to the middle, roughly. There is an experiment, roughly 80 meters underneath, where the particle beams of the LHC are
So the
colliding.
LHC is below us. How far below is it?
Well, it's, I think here, don't quote me, but I think it's one of the most shallowest point, maybe 50, 60 meters
So 60
below
meters,
ground.
we have particles firing around.
Yes.
And they're doing
And they are colliding
experiments
exactly here under these points.
Yes.
And around the collision point there is a big detector that is built. It's called LHCb, and this is what you can see here. Yeah?
Oh, right.
And the surface buildings that you see here are needed to supply the experiment with infrastructure, electricity, cooling, cryogenic gases and cryogenic liquids.
And so for the FCC, you'll have 8 of these similar structures. Is that correct? Similar sites.
For the FCC, we will have 8 sites comparable to the one that you can see here. Yes.
Okay.
The first version, electron-positron machine, will be a warm machine. So these will be warm magnets. So there's a full physics program there on the electron-positron machine. And that would take, say, 10 to 15 years to fully execute. And then we take out the accelerator and we put in a superconducting proton collider. These superconducting magnets have to be very strong, cooled with liquid helium, very high magnetic fields, technologically very challenging. The total energy in a proton-proton collision in the LHC at the moment is 14 TeV. The FCC design collision energy is 100 GeV, so really stepping up, as I say, by almost a factor of 10 to, for the moment, unimaginably impressive energies.
Well, the LHC has discovered in 2012 the Higgs particle. There are, however, several very fundamental questions about the universe and about nature and about our existence and the smallest particles and forces that hold us all together and that are responsible for the universe in the form as it is. And these questions remain still open. One of the key words in this context is, for example, dark matter. It relates to to distortions, let's say, of motions that can only be explained by the existence of a sort of matter that we do not see, that we do not understand. We cannot explain the force, we cannot explain the nature of this matter, and this makes up a huge percentage of the universe. Another of the big questions is, for example, the imbalance between matter and antimatter. You, me, the field around us, everything is made out of matter. And in the Big Bang, at the beginning of the universe, there was creation of matter and antimatter in the same quantities. So now the question is open, where has this antimatter gone? Where is the asymmetry between matter and antimatter that is responsible for us being all made out of matter?